count on you to be mine.
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
So happened on one day that a squirrel climbed on top of a flagpole. And as it was up there, the flagpole started falling down, pivoting from the point at the bottom. And here's the dilemma for the squirrel. In order to minimize the impact velocity when it hits the ground, should it jump off or go along with the ride with the falling pole? So he has two options. First, let's study that it hops off. Initially it has half times, of course, m times g times L of gravitational potential energy when the height of the pole is L. And if it just jumps down, that is converted to kinetic energy of half times mv squared. And we solve for v squared to be 2gl, hence v square root of 2gl. What about if it stays on? In that case, the system consists of the pole and the squirrel, the mass of which is pretty much just the whole m, because the mass of the squirrel is negligible compared to the mass of the pole. So to begin with, we can say that there's only the potential or gravitational potential energy of the pole, and the center of the mass of the pole defines how much potential energy it has. So in the beginning, mass of the pole times g, and what is the height of the center of gravity? That's L times 2. If you're not convinced, you can also think it in such a way that the average of the top point and the low point, their average distance from the ground is L over 2, and so you can pick a point closer to the mass of the center here and a little bit closer here, and these two also average to L over 2, and then you end up summing over the mass, and we exactly get this result. And then once we have this potential energy, that is converted now to only rotational kinetic energy of the pole, so half times I omega squared. And we calculated in the overview video that when we have a slender pole like this, the moment of inertia about the pivot point at the end is 1/3 ml squared. And what can we say about omega? Again, omega is same as the linear velocity divided by radius of the curvilinear motion or rotational motion, and in this case it's L as we go along this trajectory here. And v is of course the impact velocity, the linear velocity when the squirrel is sitting at the top of the pole. So we can substitute these expressions here, and we get mg L over 2 times half times 1/3 ml squared times omega squared, so v squared divided by L squared. And these L's cancel, and so do the masses of the pole. And we have half here and half here, And what we see is if we multiply the 3 on that side, we get 3GL equals V squared, or V squared. And in this case, the impact velocity is square root of 3GL, which is in fact larger than if the squirrel would have just jumped off.